the chain rule. There's only a couple things I want to show you. Again, I can't say it enough. As long as you're good at partial derivatives, this will be a fairly easy section. Hopefully you've noticed that just about everything we've done since I think it was 13.2 or 13.3, it was just all different uses of partial derivatives. So you really want to have your partial derivatives down because everything we've done since then involved the partial derivatives. So let's talk a little bit about the chain rule. So here's your chain rule from Calc 1. We use the chain rule when we have what we call a composite function. Basically, we're inputting one function into another. And so, f of g of x, its derivative is derivative of the outside lead the inside alone times the derivative of the inside. Now, we're going to see it written more in this Leibniz notation, dy dx equals dy du times du dx. And one of the things I want to point out about this notation, because I'm going to point it out again when we look at the chain rule in multivariable. If you were to cancel out those du's, if we're thinking of multiplying fractions, you just get dy dx. Pay really close attention to that, because if you can follow that, you can set up the chain rule. So here's our first chain rule in multivariable. So what it is, and this is the chain rule. This is the exact chain rule we used on Tuesday when I was showing you that derivation for the meaning of the Lagrange multiplier, because we had defined our objective point, our max min point, as a function of the constraint. So this would be a function of two variables, but those variables are functions of t, which means we want to take the derivative of w with respect to t. So basically, g of t and h of t are getting put in for x and y. That's the composition. So the chain rule says, okay, you do dw dx times dx dt. Notice if you cancel out the dx's, you get dw dt. And then dw dy, dy dt. You canceled out the dy's, you get dw dt. So the format should make sense in that respect. Now, sometimes you'll see these plots go along with it. I think it was in the video as well. And what these things are for, it's literally just to help you make sure that you made all the proper derivatives. All right, so if you notice the way they work, w is your initial function. Well, w is a function of x and y, so those go at the second level. X and y are functions of t, so that goes down at the third level. All right. So we're gonna do an example so I can kind of show you how this diamond works, and then we'll look at a couple other options. So we're just gonna do one from the worksheet. We're gonna look at number 4. We have that w equals u squared e to the v. So w is a function of e and v. And then we have that u is x over y, and v equals y ln of x. So here's what's happening. We're starting off with some w, right? Now w is a function of u and v. So that tells me I need to make sure I do dw du and dw dv. Okay. Now u and v are functions of x and y. So I'll have also a du dx. I'll have a du dy. I'll have a dv dy. This is going to be a little bit messy. Normally we don't label these in here, but I want you guys to see where they're coming from. And, oh, sorry, dv dx. Thank you. And then dv dy is going to be this one. because we're gonna have two partials. There's gonna be a couple options. I'm only gonna do one of them. We'll save the other one for you guys to do, because once you see one of them, guys, Chamberlain, don't make it any harder than it is. It's actually pretty easy. But I want to kind of explain how the graph here works. So let's say we want to find the WDX. All right. Well, that means I want to get from here to here. So that means I've got to do a dW du and a du dx. So dW du and a du dx. And I also have to go this way because that also gets me to x, right? I follow every path that gets me to x. So plus dW dV times dV dx. And again, here's your check. Oh, if I cancel out the du's, dW dx. Perfect. Cancel out the dV's. That's a W, kind of looks like a U there. dW dx checks out. All right. You've got this set up. The rest is just taking partials. So we just go through. So dW with respect to U is going to be 2U e to the v. U with respect to x, derivative of x is just 1. So that's 1 over y. Good. dW dV, well, derivative of e to the v is e to the v. This is just a constant. And then finally, u squared e to the v, good. And then finally, dV dx. Well, y is a constant. Derivative of ln of x is 1 over x. So, we're mostly done. Now, here's the thing. I was looking for dW dx. So I want my final answer in terms of x and y. So u's and v's need to be subbed out for what they're equal to. So 2 x over y, because u is equal to x over y. E to the y ln of x. We're going to be able to simplify that a little bit. Times 1 over y. Plus u, again, is x over y. So x over y squared. E to the y ln of x. This is already in terms of y and x. That is the derivative. That is dW dx. Now, this particular problem asks us to evaluate it at the point 1, 2. So let's see if we can simplify it a little bit and then plug that in just to see what we get. So this is 2. There's not much we can do here, but we can multiply those y's together. So x over y squared, e to the ln of x. We can bring that y up to the exponent. So e to the ln of x to the y is x to the y. You don't need to be able to do that to solve this, because when you put in the points 2 and 1, you'll still get the same thing, but that's just cleaning it up a little bit. Now here, I've got an x over y squared, but I've also got a y over x, right? So that is going to cancel out one of those. So x over y, and then this is the same thing, that's that x to the y. So if we wanted to do the w dx at the point 1, 2, we're putting in 1 for x and 2 for y. So 1 over 2 squared, 1 raised to the 2, plus 1 over 2 times 1 to the 2. We got 2 times 1/4, that's a half, so we have a half plus a half equals 1. So like I said, I'll leave the other one for you guys to try. The big thing I wanted to do is show you how the graph here, you do not have to do this, but that's how this works with the actual setting it up. You know, when it comes to preparing for the exam, You know, if you want to include one of those diagrams to remind yourself, that's fine. That's what that looks like. Okay. Questions about that one? Let's do one more while we've already got the worksheet up there. I want to take a look at number 6, which looks like it's cut up. I'm zoomed in a little bit too much. There we go. So we're going to look at number 6 too. Because I want to give you a way of thinking about these chain rule problems in more of a context. So, number 6, we have a function t that gives the temperature at any point in the xy plane measured in degrees Celsius. And so some bugs crawling around so that its position after t seconds is given by those parametric equations where x and y are in centimeters. Okay. So right now, here's what we know. T gives out temperature, x and y are inputs in terms of centimeters. But they're defined in terms of little t, which is time. So we now want how fast is the temperature rising on the bug's path at 3 seconds. So what we're looking for is the change in temperature with respect to a change in time when t equals 3. So this should spark chain rule because capital T is in terms of x and y, but x and y are in terms of little t. Well, here's what we know we can do. We can do dt dx, right? Because capital T is in terms of x and y, so we can do dt dx, and that can be multiplied by dx dt. And there's that, cancel the dx's, dt dt. Same thing with the y, dt dy times dy dt. Now, we have a couple of notations for this. Another way I could have written that is t sub x times dx dt plus t sub y dy dt. Now we're doing this at t equals 3 seconds, but look at what x and y will be when t equals 3, right? If I put, what is x going to be? X will be 2 and y will be 3, which is perfect because we're given t sub x at 2, 3 and t sub y at 2, 3. So we already know that this t sub x is 4, and we know that t sub y is 3. dx dt and dy dt we still have to find. Well, dx dt, this is a single variable calculus problem, right? This is 1 plus t to the 1/2, which is 1/2 times 1 plus t to the minus 1/2. And here, well, that's just linear. The derivative of that is 1/3. We're plugging in 3 for that guy, right? Because we're doing it at t equals 3. So 4 times 1/2, 1 plus 3, there's our 4 to the negative 1/2. 3, I'm just going to write it all out for right now. So 4 to the negative 1/2. The negative means we take the reciprocal, the 1/2 means we take the square root. So the square root of 1/4 is 1/2. So we have 4 times a half, which is 1. And 3 times a third, which is 1. Let me get to. Now we're in a context. What are the units on that 2? And if you're not sure, go back to where we started. What were the units on capital T and little t?
Celsius per second.
Okay, degrees Celsius per second. Perfect. Now remember, and this is where you got to be careful. We did have another set of units in this problem, right? Centimeters, in terms of x and y. They weren't relevant as far as our final answer because we were looking at how fast the temperature is changing with respect to time, not with respect to distance. And that's where I wanted to go through 6 so you kind of see how these pieces of the chain rule can be pulled out of these contextual problems.